Feel free to scan this QR code to see this slide. So today we are going to talk about Rust verbs. This is a Rust session for beginners, and by learning Rust verbs, we can understand Rust ownership much better. Okay, so next one. Is everyone down with this link to the slide? Anyone? Okay, if you can, please help me paste a link to the HackMD, please, so anyone can use it. Thanks. Okay, next one. Feel free to join this Slido to ask questions. I'll answer them at the end of the slide. Okay, and if you already have a link to a slide, you can click it. Okay, so let's look at the problem first. So now we have an integer, and you can print it. This is very easy. And then we introduce an inspect function to help us debug, and you will print whatever is given to it, and then return it. So we don't have to write another line of code just to be able to see it. Okay, now we change the integer to a string. Let's see what's going on. Then it breaks. It breaks in Rust. It doesn't allow you to compile. Okay, so before we explain what's going on, let's understand why an integer works. So here, it first copy the integer to an identifier, and then it moves the integer into inspect, which goes to here, and then it copies the integer to the debug macro, and then it returns the integer back to main, and then here it passes the integer to println. So it's working, and we can see it's all copied here. And so now, before we finish this one, when we are doing Rust programming, we need to understand there is a heap memory and there is stack memory. So stack memory is really good at many things. For example, it's much faster to access a stack memory, and it is also faster to allocate memory on stack, and it's also faster to drop a memory from the stack, and it also jump less. When we use stack memory, it also jump less. And heap memory doesn't have all those benefits, and it's worse. But there's one thing that makes stack memory much harder to use, is that the size of a stack memory has to be known and has to be fixed during compile time, which is not possible for some use case. For example, if we are taking input from our user, and in that case, we definitely have to use heap memory. So, and because an integer is stored on the heap, on the stack completely, so in Rust, it just copies it every time when we use it. And so in order for Rust to do copy, we have to implement a copy trait. And implement a copy trait implies it has to consist of stack-only data. And stack-only data implies it has known size and fixed size at compile time, which is not very, I would say, useful in most of the time, and also difficult to implement. Now let's look at the problem why string doesn't work. So because a string doesn't have a fixed and known size during compile time, so we have to allocate we have to allocate heap memory, and which means we have to recycle the memory. And remember, Rust doesn't have GC, zero GC. So Rust compiler has to insert the code to free memory, not too early, not too late, and not too many times, and not too few times. If we drops memory too early, there will be use after free error. And if it drops memory too late, there will be memory leak. And if it drops memory too many times, there will be double free error. And if we drop memory too few times, which means 0 times, there will be memory leak. So Rust compiler actually have to drop the memory at the right time for right times, which is very difficult. Now let's look at this. So first, it allocate a memory on a heap, and then bind to a bad beef, and then we move the data into inspect. And then we bind it again, and then we move the data into debug, and then it invalidate baby inside inspect. And this is a Rust feature. Yes, it is a feature. And then at the end of this debug macro, it will drop the memory. So baby here actually points to invalidate memory when it reaches this line. And this is why this is a very good Rust feature, because Rust already know that that won't work later, so it invalidates it beforehand. So when we try to move bad beef into the main function, it doesn't work. And it actually helped us and protected us from memory leak. So in Rust, this verb is called move. Move means change of ownership. And this is a change of ownership. Originally, it's a memory belongs to this block, but when we move it to another variable, the original one is invalidated. This is called a move. And then, so let's have a summary. So when we do Rust programming, there is stack memory and heap memory. And only stack-only data can implement a copy trait. And when we implement a copy trait, Rust will copy it. And an example of that in a standard library is a duration struct. And besides that, if a memory is on if we use a heap memory, we have to implement a drop memory or rely on it. An example of that is the vect struct in Rust. It implements a drop trait. And another example is a string in Rust standard library. It doesn't implement anything, but in the implementation of string, it is using vect to implement a linked list of string. So it doesn't have a drop, but it's relying on the drop implementation of vect to recycle memory. Okay, so you might be wondering, copy works. Why don't we just do deep copy every time, everywhere? So yes, we can actually do that. But there's no free lunch. There's no free lunch. Let's look at this. So when we copy, when we do deep copy, it actually duplicate all the data on the heap, and which can be expensive. So let's go to the next one. So Rust has another verb called borrow. So a borrow has no change of ownership. In other words, no right to drop. So let's look at this one. So we just change this ampersand. So it borrows this bad beef, and then it copies the borrow of the bad beef to debug macro. And then at the end of debug macro, bad beef is not dropped. And then back to this inspect function, it returns the pointer back to main. And then main here, you will pass it to println. And then at the end of main, it knows that it has to drop the string. So this is good. So we don't have to duplicate the data on the heap, and it's efficient. Okay. So we just added a borrow there, but actually we can borrow it before we pass to inspect, like this. And then Rust will handle the rest of it. And we can also borrow it on initialization. And so there are actually three ways to borrow and fix this problem. Which one is correct depends on the semantic of your code. You have to figure that out. And now, since we have talked about borrow, let's talk about ref. So a borrow is basically a reference, or we call it ref. And a string, take a string as an example, a string and a borrow of string is not the same. So let's take this one for example. So here, baby is a string, and we pass it to inspect. While inspect is expecting a borrow of string, and Rust just doesn't allow you to compile because they are of different types. And so you learn that they are different. But now you might be wondering, when we clone previously, why does it work? Because in the API of clone, it says it is expecting a borrow of itself. But here, we don't borrow it. What's going on? So this is a Rust feature. It's called automatic referencing and dereference. It helps you write code economically so you don't hurt your fingers. And then another type of reference is called string literal. So you might be wondering, I just say that to use heap memory, if we know its size and its fixed size during compile time. We can use hidden memory. And is it possible that we use this one because we already know the size of the string, right? So kind of in Rust we have something called string literal, and by using string literal, we don't have all the problems when we had when we deal with string. And this is a string literal, just double quotes. And there's another kind of reference. It's called string slice. So this is a string, as we previously seen. And you just add an ampersand, like a barrel, and a square bracket after it. So this means from 0 to the end of the string. So it's actually a slice of the whole string. And this is a string slice of string. And this way, we can we created a string of slice, and we can use it. So let's have a summary. So in Rust, there's reference, and there's a slice of slice. There's a slice, and there's barrel. And inside slice, we have string slice. We can also have slice of vector and array and many things. And there is a spatial type in string slice that is called string literal. Okay, so the reference. So in Rust, we can actually define a variable as mutable. And then when we use it, we can pass a mutable reference of that variable to another function, and then that function can mutate it. And take this one, for example. We just pass a mutable reference to bad beef. Sorry, we pass a mutable reference of bad beef to emphasize, and then inside emphasize, we append a question mark to the end of the string. And this will work. And here, one thing I want to emphasize is that usually you don't see operator in the left value of an assignment, but this is very common in Rust. Okay, and now I just said that a string and a barrel of string are two different types. Okay, now let's look at this example. So inspect is expecting a string literal. And here, we pass it a barrel of string. And this is working. You might be wondering why. And this is because Rust has a feature called derived coercion. So Rust will automatically convert a reference of string to the string literal. So just talk about mutable values. And here, Rust actually allows you to mutate a value without declaring it as mutable. That is to use a ref cell from the standard library, and we just define it this way, and then we pass a mutable reference of it into emphasize, and then here we call barrel mute to get a mutable reference of it, and then we dereference it, and then we append a question mark to it. And this is a pattern called interior mutability. And here, but again, there is no free lunch. You have to decide whether you want to pay the price. So when you use mute, your compiler your barrel checker runs during the compile time, and your compiler help you catch error, and there is 0 runtime cost. And it won't compile if you have any violation. And if you use ref cell, your barrel checker is running during the runtime, and you have to do code review to catch errors. And there are more runtime costs compared to using mute. And if you violate these restrictions, there will be runtime panic. So your program will crash. But then why do we use this? Because ref cells because there are use cases where Rust doesn't consider safe, but we can guarantee it's safe. by using ref cell and using code review to ensure that. And Rust doesn't prevent us from doing this kind of thing. And a ownership. So a ownership is usually it's a one-to-one relationship, but actually Rust allows us to have multiple ownership. And this is by using RC. So RC stands for reference counting, and reference counting it keeps a counter internally. So let's look at this example. So it first clone this one here, it clone it, and then increase the strong count, and then it move the clone of RC into debug, and then it drop the clone of RC at the end of debug, and then it decreases the strong count. So here, and then next line it returns it, and then at the end of main it will drop the reference to it will drop this reference count RC, this RC, and then the memory on the heap will be recycled. So this allows us to do multiple ownership. But there is also comes a cost again. So with RC, we have to catch errors during code review, and there is more runtime cost. And if there will be memory leak if we have any violation, and it is possible to have circular reference. We don't have all those problems if we don't use RC. Well, here I say improbable because we can still write circular reference using unsafe if you don't use RC. Okay, so if we have circular reference, we have to use weak to fix a circular reference memory leak. Okay, so the conclusion is to say those verbs, copy, move, clone, borrow, ref, or deref. When you are typing the equal sign, it's either copy or move. And when you type ampersand, it's either borrow or ref. And when you type asterisk, it's deref. That's it. So Q&A. So let me see if there's any question. Okay, good. There is no question. Okay, so if there is no question, we're gonna finish this one. No question, really? Okay, good. Okay, so if you are looking for a developer with this skill set, please write to this email. I'll get back to you. That's it. Thank you for joining this slide.